Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting into a quiet, far-reaching mystery, one that lives at the very edge of what we know. Ever since Einstein's theory of spacetime, a question has been quietly lingering in the background. Could space itself contain hidden tunnels, invisibly connecting distant galaxies? Could wormholes not only be real, but hiding all around us? To begin, we need to look at something deceptively familiar: space itself. Not outer space, not stars and planets, but the actual structure of space and time. In physics, this structure curves. It stretches. It flows in response to mass, motion, and energy. And because of that, it may also contain hidden folds, secret tunnels into deep space. And if those hidden pathways exist, then our understanding of the universe is only just beginning. When we picture the vacuum of space, we often imagine a vast, silent emptiness, a clean black canvas dotted with stars. But in physics, space is not nothing. It's not an absence. It's a presence. Beneath every planet, every atom, every flicker of light, there is a structure, invisible, continuous, and deeply real. We call it spacetime, a single, unified entity that combines space and time into a single four-dimensional fabric. It's not a metaphor. It's not a poetic idea. It's a literal feature of the universe. Spacetime is the framework that everything moves through, and everything moves within it because of what it is, not just where it is. Even in the deepest vacuum, there is structure. This framework has measurable properties. It has curvature. It has causal relationships. It determines how objects fall, how light bends, and how time flows. And it's not fixed. Space-time responds to the presence of matter and energy. It isn't like a grid printed on the universe. It's more like the universe itself. When a planet sits somewhere in space, it doesn't just exist in a location. It presses into the fabric, distorting the way space and time behave around it. And when that planet moves, the shape of space-time shifts with it, just slightly. The presence of mass shapes the environment, and the environment guides how mass moves in return. This interaction is the foundation of what we experience as gravity. So when we ask whether wormholes could exist, we're not asking whether holes can be punched in nothing. We're asking whether space-time, this real, flexible fabric, might be shaped into something far stranger than we've seen. And that question begins with a quiet shift in perspective. Space isn't just where things happen. It's part of what's happening. From far away, the universe looks beautifully smooth. Galaxies form elegant spirals. Clusters gather in weave-like filaments. Light travels freely through the vacuum between stars. There's a kind of calmness to the cosmic scale, a sense of order, even serenity. But that smoothness is only part of the story. Up close, things begin to ripple. Every photon carries momentum. Every particle tugs slightly on the space around it. Even in the silence between galaxies, space-time is constantly being nudged, curved, and stirred by the smallest presences of mass and motion. The surface may appear smooth, but underneath, at scales we can't directly see, the texture might be far more complex. In fact, some theories suggest that on the tiniest scales, space-time may not be smooth at all. It might be foamy, fluctuating, or even discontinuous in places. There could be microstructures, transient folds, or loops that bubble in and out of existence too quickly or too small for us to detect. At our level of resolution, these variations are invisible, like the grain of paper seen from across the room. But they could still be real. They could still shape the way things behave. And that leads to a quiet but astonishing possibility. Maybe space doesn't just have a shape. Maybe it has hidden features. Not just curves, but connections. Not just structure, but secrets. The modern view of gravity began with a transformation in how we think about space. Before Einstein, gravity was seen as a force, a kind of invisible pull that one object exerted on another. It was a useful idea, and it worked well for the motions of planets and moons. But it left something unresolved. How could this force travel across a vacuum? How could something influence something else without touching it? Einstein's answer was subtle and profound. Gravity wasn't a force at all. It was a feature of geometry. What we feel as gravity is actually just the effect of moving through curved spacetime. Imagine placing a marble on a stretched fabric. If you set a heavy object in the center, a bowling ball, say, the fabric will curve. And if you roll the marble nearby, it will spiral inward, not because the ball is pulling on it, but because the marble is following the natural curve of the fabric beneath it. This is how gravity works in general relativity. Planets, stars, and galaxies all create indentations in the shape of spacetime, and objects move not because they're pulled, but because they're falling along the paths that the geometry defines. These natural paths are called geodesics, the closest thing to a straight line in a curved world. Light follows them. Planets follow them. Even time follows them. Everything moves along these curves, shaped by the warping of the underlying fabric. It's not an illusion. It's not a model. It's the actual shape of space that governs the behavior of matter and light. And because the shape of space affects everything, understanding what can bend, fold, or connect that shape becomes central to understanding the possibility of wormholes. But what shapes that geometry in the first place? In general relativity, the curvature of space-time is determined by the stress-energy content of whatever is present. This includes mass, of course, but also momentum, energy, radiation, even pressure. Every form of energy has some influence on the shape of space, no matter how subtle. A star bends space-time profoundly. A rock does it faintly. Even the energy contained in light contributes, although in small amounts. The equations that describe this, Einstein's field equations, are surprisingly elegant. On one side of the equation is geometry, the curvature of space-time. On the other side is energy, the content of the universe. It's a direct relationship. Métis tells space-time how to curve. Space-time tells matter how to move. And the kind of curvature that results depends not only on how much energy is present, but how it's arranged. Dense matter creates strong indentations. High pressure can distort things sideways. Even a fast-moving beam of particles can create ripples or shifts in the local geometry. This flexibility means that space-time isn't just a passive background. It's an active, changing, responsive entity. It's dynamic. It listens to what's in it. And in extreme cases, like black holes or the Big Bang, the curvature becomes so intense that the very fabric of reality twists in unfamiliar ways. So if a wormhole were ever to form, it would be because space-time has been curved into a bridge, not stretched or torn, but shaped. And the first hint of whether that's possible comes from understanding these shapes in the most extreme situations. If space-time has a shape, then every object that moves through it is responding to that shape, whether it realizes it or not. In general relativity, there's no force acting on a falling object. It's not being pulled toward the Earth. It's simply following the path that space-time offers, the most efficient, natural route through curved geometry. These natural routes are called geodesics. In flat space, A geodesic is a straight line. But when space curves, whether gently or dramatically, geodesics bend with it. They don't curve because of some external influence. They curve because, from the point of view of the object, they are straight. Even a beam of light, which always moves at the same speed, will follow a curved path near a massive object, not because the light is accelerating, but because the geometry it moves through has changed. This is why orbits occur. A planet circling a star isn't being yanked sideways every instant. It's following a geodesic, a path that loops back on itself in curved spacetime. The same goes for satellites around Earth. They're not resisting gravity. They're falling freely through a curved environment, tracing out the most natural paths that the universe allows. And this principle doesn't just apply to objects. It applies to time itself. Clocks run at different rates in different parts of curved spacetime. A clock on the surface of Earth ticks slightly more slowly than one in orbit. This is not an illusion. It's a real consequence of how time stretches and compresses under the influence of gravity. GPS satellites have to correct for this constantly. If they didn't, their signals would drift out of sync within minutes. So geodesics aren't just about motion. They're about the flow of time, the behavior of light, the rhythm of causality. They're the threads along which reality moves. And when we start imagining wormholes, we're imagining an even stranger possibility. Could the shape of space-time allow two geodesics, two seemingly separate paths, to meet somewhere unexpected? Could there be a hidden connection, not visible from the outside, but real from within? This brings us to one of the most compelling ideas in physics, the possibility that space could be multiply connected, that instead of being smooth and continuous in the way we expect, space could contain hidden links, places where two distant regions are, in fact, directly adjacent from the inside. Imagine folding a sheet of paper so that two faraway points touch. On the surface, the paper still looks flat. If you only walk along its face, the journey from one point to the other takes time. But in the third dimension, the dimension into which you folded it, the 2 points are already side by side. Wormholes are like that, but in space-time. They aren't tunnels carved into matter. They're connections between regions of space, made possible by the way space-time curves in higher dimensions. From the outside, there's no indication they exist. No visible gap, no rip in the starscape. But from within, the geometry could be radically different, a shortcut that bypasses the distance in between. If such a structure existed, it would be completely invisible to someone who never enters it. It would appear as two separate locations in the universe, just as far apart as expected. Only by stepping inside would you discover the truth, that the gap has been collapsed, that two places are really one. Physicists refer to this as non-trivial topology, the idea that space can have hidden shapes, connections, or features that aren't apparent from the surface. A coffee mug and a donut are topologically the same. They both have one hole. In curved space-time, the holes might be invisible, not gaps in material, but bends in geometry. And if such folds or bridges exist, then the structure of space is not only curved, it's connected, secretly, silently, and maybe far more intimately than we've ever imagined. The idea of a wormhole didn't begin with science fiction. It began with a question buried deep inside Einstein's theory of general relativity, a question about how space and time behave near the edge of a black hole. In 1935, Albert Einstein and Nathan Rosen were studying a particular solution to Einstein's own equations, one that described the region outside a spherical mass, like a non-rotating black hole. It's known as the Schwarzschild solution, and it revealed something unexpected. The geometry of spacetime near such an object didn't just curve, it folded back on itself in a very peculiar way. Einstein and Rosen realized that this solution contained two identical copies of space, connected at a single point, a kind of bridge. To visualize it, imagine two separate universes, each with their own stars and galaxies, joined together at one location by a throat-like connection. They called this structure an Einstein-Rosen bridge. It wasn't science fiction. It was a direct mathematical consequence of general relativity. But it raised a strange possibility. Could space really do that? Split into two regions and connect them through a tunnel? At the time, Einstein wasn't interested in faster-than-light travel or alternate universes. His motivation was entirely different. He hoped this model could help describe fundamental particles without relying on singularities, the infinitely dense points that appear in simple black hole models. For him, the bridge was a way to avoid those infinities. But others would later see it as something more, a possible path through space and time. Still, there was a problem. The bridge wasn't stable. According to the math, it would pinch shut too quickly for anything to cross from one side to the other. It existed only for an instant, not in physical time, but in mathematical space. A ghost of a connection. To understand why, we need to look more closely at the Schwarzschild black hole and what it really represents. The Schwarzschild solution is one of the simplest and most elegant solutions to Einstein's equations. It describes a spherical object with mass, no charge, and no rotation. It works beautifully for stars and planets, and it also predicts the existence of black holes, regions of space where gravity is so intense that nothing, not even light, can escape. But when we examine this geometry carefully, something strange appears. The coordinates that describe space near a black hole begin to behave oddly. At a certain radius, the event horizon, the roles of space and time seem to switch. Inside the horizon, no path leads outward. All geodesics point inward, as if the entire interior is collapsing toward a central point. This is the singularity, the place where the curvature becomes infinite and our current theories break down. But just outside this boundary, the structure of spacetime is still well-defined. And according to the math, it isn't just one region, it's two. The Schwarzschild solution describes two separate sheets of spacetime, mirrored across the black hole's horizon. In the extended version of the solution, these sheets are connected by a bridge, a tunnel through the interior that joins them together. From the outside, both sheets appear identical. Each has its own version of the black hole, but they aren't physically the same place. They are mirror images, joined only at the throat. This connection, the Einstein-Rosen bridge, exists not because matter dug a tunnel, but because the geometry of space allows for such a shape. It's a product of pure curvature, a mathematical object with a peculiar property. It links two places that should be separate, but aren't. Still, like the original model Einstein proposed, this structure collapses too quickly to allow anything through. It's a bridge in theory, not in practice. But even so, the idea had been planted. And as physicists continued to explore the implications of general relativity, they began to ask a new question. What would it take to hold that bridge open? If a black hole marks a point of no return, a place where space curves inward so steeply that nothing escapes, then it's natural to ask, could there be the opposite? A region of space that can only emit, never absorb. This hypothetical object is called a white hole, a solution to Einstein's equations that mirrors a black hole in reverse. Where a black hole pulls everything inward, a white hole pushes everything out. Nothing can enter it. Matter and light can emerge, but not return. In the extended geometry of the Schwarzschild solution, the same solution that gave us the Einstein-Rosen bridge, a white hole appears naturally as part of the full structure. One side of the wormhole leads to a black hole, the other leads to a white hole. They're not separate entities. They're two ends of a single mathematical shape. But white holes are strange. No one has ever observed one. They violate thermodynamic expectations. And in the real universe, there's no known process that would create them. They seem unstable, destined to collapse as soon as any perturbation occurs. A single photon falling into a white hole would, in theory, destroy it. Still, as an exit point from a wormhole, the concept has its place. If you could somehow enter one end, the black hole side, and traverse the throat before it pinched shut, the white hole would be your emergence. An impossible escape. A one-way door from elsewhere. But there's a catch. Even in the best-case scenario, these wormholes seal themselves almost instantly. There's simply no time to cross. This limitation isn't just a technicality, it's a fundamental feature of the solutions themselves. In the Einstein-Rosen bridge, the throat connecting the two regions closes before anything can pass through. This happens because the geometry is unstable. The moment any matter or energy tries to enter, it disturbs the shape of spacetime, and the bridge collapses. This isn't just a problem of materials or scale. It's baked into the mathematics of general relativity. The structure is delicate. It relies on perfect balance, perfect symmetry, and the absence of anything that might shift its weight. It's like trying to walk across a bridge made of reflections. The instant you try to touch it, it disappears. And so, early models of wormholes were dismissed, not because they were mathematically invalid, but because they were physically unreachable. They existed in the equations, but they offered no passage, no crossing, no hope of contact. Still, that idea, a shortcut through space, refused to vanish. The possibility remained, waiting for a new perspective. One that would come not from classical physics, but from the strange possibilities of quantum theory. And from a new question, even more curious than the first, what if we could keep a wormhole open? The core idea behind a wormhole is surprisingly simple: a shortcut through space-time. In ordinary space, the shortest path between 2 points is a straight line. But if space can bend, then that rule no longer holds. Just as you might cut across a folded map instead of walking along its surface, curved space might offer routes that seem impossible if you only look from the outside. In this view, a wormhole isn't a tunnel carved through something solid. It's a connection formed by the shape of space itself, a kind of bridge between distant regions that lets you skip the intervening distance. From the inside, the journey could be brief. From the outside, the 2 points might appear impossibly far apart. This is what makes wormholes so fascinating. They don't violate the speed of light. They don't require breaking any known physical laws. Instead, they offer a quiet loophole, a change in the shape of the playing field, rather than the rules that govern motion within it. But such a shortcut would require a very specific kind of geometry. The curvature would need to be extreme, yet stable. The connection would need to form and persist long enough to matter. The bridge would need to be smooth, traversable, and resistant to collapse. This is where theory runs into difficulty. The Einstein-Rosen bridge is not traversable. Other known solutions tend to collapse instantly or contain singularities. To go further, physicists began to wonder not just whether these shapes could exist, but whether nature itself might ever create them. Could the universe form a wormhole on its own? It's not an easy question to answer. In general relativity, wormholes require highly unusual conditions, specific distributions of energy, pressure, and momentum that are rarely, if ever, found in nature. Most known solutions are unstable or require something exotic to keep them from collapsing. But the universe is full of extremes. In the hearts of black holes, space-time reaches unimaginable densities. Near the Big Bang, the entire cosmos was compressed into a region smaller than an atom. In neutron stars, atomic nuclei press so tightly together that entire mountains can form from a single cubic inch of matter. If a wormhole could form spontaneously, it might happen in one of these places, where geometry is already pushed to its limits. Some theorists have speculated that in the early universe, brief connections between regions of space could have flickered into existence, held open for a moment by violent fluctuations in density and pressure. Others suggest that black holes themselves might contain bridges, not to other universes, but to other regions of our universe. A path not outward, but sideways, from one pocket of space-time to another, hidden inside the curvature. And then there are quantum theories, which propose that space-time isn't smooth at all. If the fabric of reality is foamy at the smallest scales, then perhaps tiny wormholes are forming and collapsing all the time, too small to detect, but real nonetheless. These would be microscopic connections, not big enough to travel through, but enough to suggest a universe more tangled than it appears. Still, none of this is proof. We've never observed a wormhole. We don't know how to make one. And the conditions required to create them, as far as we know, are far beyond anything we can reproduce. But the question remains open, quietly suspended in theory. If a wormhole ever did form, even for a moment, what would we find on the other side? Up to this point, most of the wormholes we've encountered, at least in theory, tend to collapse. They exist fleetingly or not at all. The throat pinches shut. The curvature becomes too extreme. The connection fails before it can be used. But what if a wormhole could be held open? To do that, something would have to resist the crushing inward pull of gravity, not just momentarily, but continuously. You would need something to push outward against the natural tendency of space-time to close the throat. And ordinary matter won't do it. Anything with mass, anything familiar, dust, plasma, even light, only adds to the inward pull. It makes the situation worse, not better. What's needed is something truly strange. Something that bends space-time in the opposite direction. Something that creates repulsive gravity. In theoretical physics, we call this exotic matter. Exotic matter isn't just matter that's unfamiliar. It refers specifically to material, or energy, that has negative energy density. Not zero, not low, but less than nothing. In the equations of general relativity, negative energy curves space in the opposite direction from normal mass. Instead of pulling things inward, it pushes them apart. This is not science fiction. Mathematically, general relativity allows for negative energy. But physically, it's another story. We don't know if negative energy can exist in large amounts, or whether it could be collected, manipulated, or sustained. But if it could, then in theory, it might be enough to prop open the throat of a wormhole. Think of it like scaffolding, an invisible brace holding the tunnel apart from within. Exotic matter wouldn't pull the wormhole closed. It would hold it open, keeping the geometry from collapsing back in on itself. In fact, it's not just helpful, it's essential. Without negative energy, no known model of a traversable wormhole can survive for more than a moment. But is there any hint that negative energy is real? In fact, there might be. In the vacuum of space, even in the absence of light or matter, there are still quantum fluctuations, tiny, unpredictable blips of energy that appear and vanish too quickly to be seen. These fluctuations are baked into the uncertainty of quantum mechanics. Even empty space can never be completely still. And in certain carefully arranged situations, these fluctuations can produce something measurable, a very small but very real region of negative energy. This was demonstrated in the 1940s through a phenomenon now known as the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, just a few nanometers apart, they experience an attractive force, as though something is pushing them together. But there's no electricity, no magnetism, no particles in between, just vacuum. The explanation lies in the quantum fields that permeate space. Outside the plates, all possible wavelengths of quantum fluctuations can exist. But between the plates, only certain wavelengths are allowed. The mismatch creates a pressure imbalance, more energy outside than inside, which results in a tiny but detectable push. And this effect implies that the space between the plates has less energy than the space outside. It is, in a sense, negative compared to the vacuum. Not in an abstract way, but in a measurable, physical one. This is the first real hint that negative energy is more than just theoretical. It exists, at least briefly, at very small scales. The Casimir effect doesn't give us a lot of it, and it's not easy to scale up. But it shows that the universe allows, under the right conditions, regions of space that contain less than nothing. And if that's true, even fleetingly, then maybe, just maybe, the building blocks for a traversable wormhole are already here. Not in science fiction, not in another galaxy, but in the fabric of space itself. In 1988, physicists Kip Thorne and Michael Morris published one of the first serious studies of traversable wormholes. Wormholes that, in principle, could be crossed by people or signals without path, destroying either the traveler or the tunnel itself. Their work wasn't about proving such things existed. It was about figuring out what it would take to make one possible. They started with general relativity and asked a simple question. If we wanted to design a wormhole that someone could pass through, slowly, safely, without extreme forces or time distortions, what kind of space-time char would we need? The result was the Morris-Thorne wormhole, a carefully constructed solution to Einstein's equations that describes a smooth tunnel between two distant regions of space. The tunnel is stable, non-singular, and has no event horizon. That means you could go in and come back out. But the catch is what's inside. To keep the throat of the wormhole open, the solution requires negative energy density, and not just a little, a significant amount, carefully arranged. The exotic matter must occupy the inner region of the wormhole and must push outward with enough pressure to resist collapse from all directions. In this model, space isn't being torn or punctured. It's being shaped, curved in a very specific way. The wormhole geometry is carefully crafted to allow safe passage. There are no infinite forces, no deadly singularities, but it only works if negative energy is present in just the right configuration. In other words, general relativity allows for traversable wormholes, but only with help. Nature has to provide the structure. Something has to hold it in place. This need for exotic matter raises a deeper issue. It's not just about difficulty, it's about violating assumptions baked into the laws of physics. Specifically, traversable wormholes appear to violate what are called energy conditions. These are principles that general relativity usually assumes to keep space-time well behaved. They forbid certain kinds of bizarre energy distributions, like infinitely dense points or negative masses, and help ensure that cause leads to effect, and that gravity behaves in predictable ways. The null energy condition, for example, requires that light rays always converge under the influence of gravity, something that's true in almost all classical situations. But exotic matter, by definition, breaks this condition. It causes light rays to spread apart, or even diverge, as if gravity has turned repulsive. Breaking these rules doesn't make the math invalid, but it does raise questions. Does nature permit this kind of behavior? Or are these solutions mathematical curiosities, forbidden by deeper principles we don't yet understand? Some physicists argue that quantum mechanics already shows us that the energy conditions can be violated, at least locally and temporarily. Others think that any structure requiring such violations might be unstable or short-lived, unable to persist without constant input or precise balance. But the fact remains, the only known way to keep a wormhole open involves something that challenges the very assumptions that make physics predictable. That doesn't mean it's impossible, but it means we're far outside the world of ordinary matter and deep into the unknown. The possibility of a stable, traversable wormhole raises not just engineering questions, but profound questions about time itself. If a wormhole connects two distant regions of space, and if each mouth can move independently, then under the right conditions, it might also connect two different points in time. Imagine this: one end of the wormhole stays still, while the other is accelerated to near the speed of light and brought back again. Due to time dilation, a real effect confirmed by countless experiments, the moving mouth will have aged less than the one that stayed behind. And now, the wormhole connects not just distant places, but different moments. Enter through one mouth and you arrive in the past. Exit through the other and return to the future. In principle, a wormhole could become a time machine. This leads to what physicists call closed time-like curves, paths through spacetime that return to their own beginning. They're allowed by the equations of general relativity, but they create a host of paradoxes. What happens if you go back and change something that prevents the trip from occurring? Could information, or objects, loop endlessly with no origin? To address these puzzles, physicist Stephen Hawking proposed the idea of chronology protection, the notion that the laws of physics might somehow prevent the formation of time machines. Perhaps quantum effects destabilize the wormhole. Perhaps vacuum fluctuations grow uncontrollably. Perhaps something always happens to close the door before time travel begins. We don't know if such protection exists. But the moment we imagine a wormhole that stays open, we're not just bending space, we're bending causality. And that makes stable wormholes even stranger than they first appear. Despite these difficulties, the question persists. Could a stable wormhole form, either in nature or through technology? We've seen that general relativity permits the geometry. We've seen that quantum mechanics hints at the exotic energies required. But that's still far from knowing whether such things could ever exist outside the equations. In nature, there are few places where the required conditions might arise. The early universe, dense, chaotic, and far beyond the energy scales we can recreate, they have briefly supported wormholes, if only for tiny fractions of a second. Some inflationary models suggest the rapid expansion of space could have left behind small topological defects, tunnels, tubes, or loops embedded in the vacuum. These wouldn't be large enough to travel through, but they would show that space can connect in strange ways. More speculative ideas involve advanced civilizations. If a species had access to vast amounts of energy and an understanding of both quantum field theory and general relativity, could they construct or stabilize a wormhole? Could they generate negative energy, shape the curvature of space, and prevent the throat from collapsing? It's impossible to know. But the physics we have suggests that any such endeavor would require technologies far beyond anything we can conceive, and control over matter and energy on a scale we've never seen. Still, theorists continue to explore the possibilities. New papers are published every year. Some propose new metrics, new stabilizing forces, or new interpretations of quantum gravity that might allow for long-lived wormholes without violating fundamental laws. And even if no one ever builds one, even if they remain forever out of reach, their existence as logical consequences of our best theories keeps the idea alive. Not because we're certain they're real, but because, so far, nothing has proved they're not. Up to now, we've been looking at wormholes as vast, high-energy structures, something that might stretch across space or form in the hearts of stars. But there's another possibility, a quieter one that hides not in the vastness of the universe, but in its smallest, most secret places. To find it, we have to shrink. Not just to the scale of atoms or particles, but beyond that to the Planck scale, the smallest meaningful scale in physics. At this level, a trillion times smaller than a proton, the very notion of smooth space begins to break down. In classical physics, space is a continuous backdrop. You can zoom in forever and still find more space in between. Though quantum mechanics doesn't work like that. It deals in probabilities, uncertainty, and discreteness. And when we combine quantum mechanics with general relativity, two theories that don't naturally agree, something strange happens to space-time itself. According to many approaches to quantum gravity, the fabric of space-time becomes turbulent at the Planck scale. It fluctuates. It writhes. Tiny distortions appear and vanish like bubbles in boiling water. This seething chaos is sometimes called quantum foam, a term coined by physicist John Wheeler in the 1950s. In quantum foam, space-time isn't smooth at all. It's alive with temporary fluctuations in curvature, tiny warps, little loops, momentary holes. The geometry shifts constantly, too fast and too small for any of our instruments to detect. We don't know exactly what this looks like, because we don't yet have a complete theory of quantum gravity. But whatever form it takes, the implication is profound. At the deepest level, space-time might not be flat or calm. It might be wild. And in that wildness, wormholes may already exist. These wouldn't be the kinds of wormholes we see in science fiction. They wouldn't be big enough to walk through, or even to send a particle. They'd be incredibly tiny, perhaps only a Planck length across. But they would still count. They would still be real, if only for a fleeting moment. In fact, some theorists suggest that quantum foam may be riddled with microscopic wormholes, constantly forming and collapsing, connecting points in space that are otherwise far apart. These connections wouldn't last long. They might only exist the billionths of a trillionth of a second. But if the universe allows them, it would mean that space-time is not just dynamic, but multiply connected at the smallest scales. This kind of connectivity isn't something we can measure directly, but it could still affect how particles behave. Quantum entanglement, tunneling, even the structure of black hole interiors, all might be shaped, subtly, by the presence of these tiny links. The vacuum wouldn't be empty. It would be entangled, curved, and quietly stitched together by wormholes too small to see. It's important to be cautious. These are still speculations. We don't yet have experimental access to the Planck scale, but mathematically, the idea fits. And if space-time is granular and chaotic at the smallest level, then wormholes might not be rare at all. They might be everywhere, all around us, in the structure of space itself. The idea that space-time might contain tiny wormholes isn't just poetic, it comes from serious attempts to unify the deepest laws of nature. At the heart of this effort lies the search for a theory of quantum gravity, one that combines quantum mechanics with general relativity into a single, coherent framework. This has proven incredibly difficult. Quantum mechanics is probabilistic, focused on tiny scales and discrete energy levels. General relativity is continuous, geometric, and smooth. When you try to apply one to the domain of the other, say the quantum mechanics of a black hole or the curvature of space at atomic distances, the mathematics breaks down. But one guiding idea has emerged again and again. Maybe space-time itself is not continuous. Maybe, like energy levels in an atom, space is quantized, made of discrete, indivisible units. This doesn't mean there's a grid or a background lattice. It means that beyond a certain scale, space stops behaving like a smooth fabric and starts behaving like something more granular, a mosaic of tiny units of volume, stitched together by quantum rules. Time, too, might come in discrete steps rather than flowing continuously. In such a world, the foaminess of space-time isn't just a side effect, it's a fundamental property. And the bubbling, shifting geometry we imagined at the Planck scale might be the true nature of reality. One of the most developed approaches to this idea is called loop quantum gravity. It proposes that space-time is made up of loops, tiny quantized threads that form networks, like a web woven through the universe. These loops define areas and volumes, not through smooth curves, but through combinatorial structure, a kind of quantum scaffolding. According to loop quantum gravity, the geometry of space arises from these connections. There's no background space in which they sit. The network is space. This picture replaces the smoothness of classical geometry with something deeply textured. Where general relativity gives us curvature and continuity, loop quantum gravity gives us nodes and links, and a new sense of what it means for two places to be connected. In this framework, the idea of a wormhole becomes more natural, not as a vast tunnel, but as a shortcut across the network, a direct link between distant nodes, a fold not in a fabric, but in the structure of relationships themselves. These connections wouldn't look like holes. They wouldn't be visible at all, but they could change the way information moves. They could even explain some of the strange correlations we see in quantum physics, patterns that suggest particles know more about each other than space should allow. If loop quantum gravity is right, if space is fundamentally made of loops, then the universe may already be full of shortcuts, not big enough to walk through, not strong enough to stabilize, but real, quietly real. In 2013, a striking idea began to take shape in the world of theoretical physics, one that suggested a deep connection between two of the strangest concepts in modern science. On one side was entanglement, the quantum phenomenon in which two particles become so deeply linked that measuring one instantly affects the other, no matter how far apart they are. On the other side was the Einstein-Rosen bridge, the theoretical wormhole that connects two regions of space-time through a hidden tunnel. The proposal, known simply as ER equals EPR, came from physicists Juan Maldacena and Leonard Susskind. Their suggestion was bold. Perhaps every pair of entangled particles is connected by a tiny wormhole, not one that matter can pass through, not a tunnel in space, but a geometric link, a subtle structure in space-time that encodes the connection we see as entanglement. The name ER equals EPR comes from two famous papers. ER stands for Einstein-Rosen, the bridge connecting two sheets of space. EPA stands for Einstein-Podolsky-Rosen, the paradox that first questioned how entanglement could work without violating causality. The idea behind ER equals EPR is that entanglement is geometry. That when two particles are entangled, they aren't just correlated, they're joined. And the thing that joins them is a wormhole, too small to see, too fleeting to use, but real enough to define their relationship. This doesn't mean you can send messages faster than light. The wormholes aren't traversable. But it means that spacetime itself may encode quantum relationships through its shape. The foaminess of the vacuum, the texture of quantum space, might not just be random. It might be laced with hidden links, connections that reflect the fabric of entanglement beneath our measurements. If ER equals EPR is true, then spacetime is not a smooth container with quantum fields inside it. Spacetime emerges from entanglement. It is the quantum connections. This is still a hypothesis, and much about it remains unproven. But it's one of the most exciting ideas in modern theoretical physics, not because it answers everything, but because it ties together questions that were once thought to be separate. And it leads to a gentle, astonishing thought. What if wormholes are not rare? What if they are everywhere? If each entangled particle pair is connected by a tiny Einstein-Rosen bridge, and if entanglement is as widespread as we believe, then spacetime might already be full of wormholes. Not big ones, not stable tunnels between stars, but tiny, transient structures that thread the universe together like threads in a woven cloth. In this view, wormholes are not anomalies. They are the rule, the natural consequence of quantum connectivity. And if spacetime is made from these connections, if its shape is determined by the relationships between things, not just their locations, then wormholes might not be things at all. They might be how space holds itself together, how distances become meaningful, how causality emerges from chaos. We still don't know whether this picture is right. We can't see the Planck scale directly, but the math points in this direction. And the deeper we go into quantum gravity, the more it seems that space is not a backdrop, it's a web of hidden relationships. And hidden in that web, the wormholes may already be here. If wormholes are real, even tiny, transient, or rare, then the next question is simple. Could we detect one? Is there any way to know if the fabric of space has folded right in front of us? To answer that, physicists have turned their attention to gravitational lensing, the way massive objects bend light from more distant sources. It's one of the clearest predictions of general relativity, and one of the most beautifully confirmed. A galaxy, or even a cluster of galaxies, can act like a lens, bending and magnifying the light of galaxies behind it. Sometimes, the result is a distorted arc. Sometimes, a full ring. Sometimes, multiple images of the same object appear in different places. This bending occurs because light follows geodesics, natural paths, through curved spacetime. If the spacetime is warped, the light curves with it. So what would happen if that curvature came not from mass, but from a wormhole? In theory, a wormhole could produce gravitational lensing just like a galaxy or black hole, but with a different signature. The light might not just be bent, it might be duplicated in a strange way. The wormhole could bend light from two entirely different regions of the universe, sending both beams to the same observer. You could see a star that doesn't exist where it appears. Or a duplicate of a galaxy, shifted or inverted. You might even see a flash of light from something far away that was never emitted in your direction. Physicists have developed models for how wormholes would distort light, how their lensing patterns might differ from ordinary gravitational sources. These patterns could be asymmetric, unstable, or subtly warped in a way that no star or black hole could produce. In other words, wormholes might have optical fingerprints. We just have to learn how to recognize them. And that leads to a provocative idea. Maybe we've already seen them. The universe is filled with strange gravitational lenses. Some are clean and symmetric, but others defy easy explanation. Odd arcs, bright spots with no clear source, lensing events that flicker or repeat in unexpected ways. These anomalies are rare, but they exist. And while most can likely be explained by overlapping objects or dark matter distributions, a few remain open questions. In 2007, a team of astrophysicists proposed that a particular set of double-imaged quasars might be the result of wormhole lensing. Others have speculated that some dark matter halos, which bend light but contain no visible matter, could be wormholes masquerading as invisible mass. There's no definitive evidence yet, but the sky is full of light that has been bent, curved, and twisted on its journey to us. And somewhere in that maze of distortions, a wormhole could be hiding. Of course, we have to be cautious. Science demands more than imagination. It demands confirmation, replication, and rule-outs. But it's not unreasonable to think that if wormholes exist, even rarely, they might leave behind a visible trace. Not a portal, not a tunnel, but a subtle ripple in the paths that light takes across the cosmos. A hidden lens, a quiet echo, a piece of sky that doesn't quite make sense. If wormholes don't form naturally, or if they collapse too quickly to be useful, could someone, somewhere, build one? This is the realm of cosmic engineering, a kind of speculative physics that asks not what we can do now, but what might be possible for a civilization millions of years ahead of us. One that has harnessed not just electricity and chemistry, but space-time itself. In principle, the requirements are clear. To build or stabilize a wormhole, you need to manipulate gravity, not just to bend it, but to shape it precisely. You need to control negative energy, possibly through quantum fields, Casimir-like configurations, or some mechanism we haven't yet discovered. You need to maintain this exotic matter in just the right distribution, pushing outward against the natural collapse of the tunnel. And you must do it all in a way that preserves stability, avoids singularities, and keeps tidal forces within tolerable bounds. It's not just a question of technology, it's a question of energy. The scales involved are vast. Even holding open a microscopic wormhole would likely require more energy than any civilization on Earth has ever produced. A traversable, human-scale tunnel might require the energy equivalent of an entire star, or more, condensed and arranged in ways we can barely describe, let alone build. But if such a civilization existed, if it had mastered quantum gravity, built machines the size of solar systems, and tamed forces we now call exotic, then constructing or stabilizing a wormhole might not be out of reach. In fact, some scientists speculate that if wormholes exist at all, and if they're traversable, then they may already be artifacts, created intentionally, not formed by chance. They might be relics of a civilization that found a way to stitch space together, not for exploration or conquest, but for survival, or perhaps for something else entirely. If we ever encountered one, by accident or design, the next question would be even stranger. Could we pass through it? Theoretical models suggest that traversing a wormhole would require care. Extreme care. The throat, the narrowest part of the tunnel, must be stable enough to resist collapse. The traveler must remain inside the safe zone, avoiding tidal forces that could stretch or compress the body beyond survivability. The geometry must be navigable, with a smooth path from entrance to exit. And the ends must remain synchronized, avoiding time distortion so severe that return becomes impossible. Some models predict intense gravitational gradients, places where time slows dramatically, or space curves unpredictably. A person passing through would experience strong time dilation, just like near a black hole. In some scenarios, it might take seconds inside the tunnel, but years outside. Or the reverse. Radiation might also be an issue. As the traveler moves through the wormhole, stray particles, even light, could be blue-shifted to dangerous energies. Shielding might be necessary. So might careful trajectory planning, constant field stabilization, and compensation for quantum effects that could destabilize the tunnel mid-transit. And even if all of that was solved, if the wormhole were perfectly stable, with no harmful effects, the simple act of stepping inside would remain an astonishing moment. One instant, you're in one place. The next, you're somewhere else, without crossing the space in between. A doorway not just through distance, but through the shape of the universe itself. Wormholes have become familiar in science fiction. Shimmering tunnels, glowing rings, instant gateways between planets or galaxies. They hum with light, flare with energy, and whisk characters across the cosmos in seconds. But the physics behind real wormholes is far stranger and far quieter. A traversable wormhole, if it exists, wouldn't look like a hole in space. It wouldn't be visible at all unless something entered or exited. Its mouth might resemble a sphere, floating silently, distorting light like a lens. Or it might be completely dark, detectable only by its gravitational influence. There'd be no swirling colors, no roaring tunnel. From inside, the passage would feel uneventful, like moving through still air. No motion is required, no propulsion. The traveler wouldn't feel a rush. They'd simply step in and step out, somewhere else. Time might behave oddly. Clocks could desynchronize. Gravity could shift. But there would be no sound, no resistance, and no cinematic spectacle. Just geometry. Just space itself, shaped into a bridge. And if wormholes are real, even nearby, we might never know, unless we learn how to look. That raises a quiet, compelling question. Why haven't we found one? If wormholes exist in our universe, even in rare or hidden forms, why haven't we seen signs? Gravitational lensing, unexpected time delays, duplicate images, or strange distortions in space? There are several possible answers. First, wormholes might be too small. If they exist at the Planck scale or only slightly larger, they'd be undetectable with any current technology. Even with sensitive gravitational wave detectors or precision telescopes, we'd miss them entirely. Second, they might be too unstable, forming and collapsing before light or matter can pass through, appearing briefly in the quantum foam and vanishing without a trace. In this case, they wouldn't leave behind lasting evidence. Third, they might be camouflaged. A wormhole could bend light and gravity in ways that mimic more ordinary objects, like dark matter clumps, compact stars, or galactic halos. Without knowing what to look for, we might see the signs, but mistake them for something else. Fourth, they might be rare. A relic of the early universe, formed in extreme conditions that no longer exist. If only a few wormholes ever formed, they could be hiding far away, behind galaxies, inside black holes, or even between cosmic voids. And finally, they might be hidden by design. If a wormhole was constructed, not by nature, but by intelligence, it might be protected, shielded, or placed where it won't be easily found. It might be locked to certain energy levels, or visible only under specific conditions. It might not even be part of our universe in the usual sense. We simply don't know. But the absence of evidence is not the same as evidence of absence. The silence doesn't mean they aren't there. It means we haven't yet found the right way to listen. And so the search continues, not just in telescopes, but in theory. Not just in starlight, but in equations. Quietly, carefully, the question remains open. The most honest answer to the question, do wormholes exist, is also the most mysterious. We don't know. Not because they've been disproven. They haven't. Not because they break the rules. They don't. At least not in every scenario. But because the universe has not yet given us clear evidence. No signal. No unmistakable pattern. No observation that says, without doubt, this is a wormhole. And yet, everything we've built in this journey, general relativity, quantum field theory, speculative models, and cosmological observations, points to the possibility. Not the certainty, but the opening. The quiet, maybe. Wormholes aren't just science fiction ideas. They're allowed solutions to Einstein's equations. They arise naturally from quantum geometry. They're consistent with entanglement. They even appear in black hole thermodynamics and in modern theories that attempt to unite gravity with quantum mechanics. No one has proven that wormholes must exist, but no one has proven that they can't. That alone makes them one of the most fascinating frontiers in theoretical physics. They lie at the boundary, not between truth and falsehood, but between what we understand and what we don't yet know how to test. So, if we wanted to look for one, carefully, patiently, without assuming too much, what kind of evidence might we hope to find? One possibility is gravitational lensing anomalies. As we saw before, wormholes could bend light in unusual ways, producing unexpected images, distorted arcs, or sudden shifts in brightness. By carefully analyzing the sky, especially in regions where mass seems to be missing or duplicated, astronomers might catch a glimpse of a lens that behaves unlike any known object. Another possibility lies in gravitational wave signals. When two massive objects collide, like black holes or neutron stars, they release ripples in spacetime. These waves carry detailed information about the collision. If a wormhole were involved, either as a conduit or as a participant, the resulting waveform might show unexpected echoes, time delays, or frequency shifts that differ from standard templates. Some researchers have proposed searching for these echoes in the tails of gravitational wave events. If they exist, and if they match the predicted patterns, it could hint at exotic structures hiding near compact objects. There's also the idea of energy condition violations. Most forms of matter obey certain rules, like having positive energy density. But exotic matter, needed for traversable wormholes, violates these conditions. If we found regions where energy behaves strangely, where light speeds up instead of slows down, or where radiation curves oddly, it could suggest the presence of unusual space-time geometries. More subtly, there's the concept of entanglement patterns. If wormholes and entanglement are related, as ER equals EPR proposes, then the structure of quantum correlations might reflect space-time connectivity. By studying how particles are entangled across long distances, especially in black hole evaporation, or in highly correlated quantum systems, we might learn something about the underlying geometry of space. And finally, we could look at the motion of stars and gas. If an object orbits something that's invisible but doesn't behave like a black hole, doesn't emit radiation, doesn't collapse, and exerts unusual tidal forces, it could hint at a wormhole. Some galactic cores or dark matter halos might eventually show this kind of behavior. These are not easy observations. They require precision, patience, and the courage to look for signs of the unfamiliar. But science is always a balance between skepticism and curiosity. And the search for wormholes is no different. If they're out there, they may not announce themselves. They may appear only in patterns, in the way light bends, waves echo, or particles correlate. But to those who know how to listen, the silence might not be empty. It might be full of hidden structure, waiting to be seen. Some of the most intriguing hints about wormholes come not from observation, but from a highly abstract idea in theoretical physics known as the holographic principle. This principle suggests that, in some cases, a theory of gravity in a volume of space can be exactly equivalent to a theory without gravity on the boundary of that space, a kind of dual description, where everything that happens in 3 dimensions can be fully described by a 2-dimensional surface. This idea was made concrete in a framework called ADDS/CFT, short for Anti-der Sitte space/conformal field theory. In ADS/CFT, a gravity theory in a curved space with a negative cosmological constant, Anti-der Sitte space, is mathematically equivalent to a quantum field theory on the boundary of that space. It's a strange and beautiful idea. It tells us that space-time and gravity might emerge from something entirely quantum and lower dimensional. And wormholes, remarkably, appear naturally in this framework. In some holographic models, a wormhole connecting 2 black holes in the bulk space corresponds to quantum entanglement between the 2 systems on the boundary. The wormhole is not just allowed, it's required by the entanglement structure. If the 2 sides are maximally entangled, the geometry must include a connecting bridge. This gives mathematical weight to the ER equals EPR idea. It suggests that entanglement is not merely correlated behavior, it's a kind of glue that holds space-time together. The wormhole, in this case, is not a tunnel for travel, but a manifestation of quantum relationships. We still don't live in an Anti-der Sitte universe. Our cosmos has a positive cosmological constant, not a negative one. But many physicists believe that insights from ADDS/CFT may still apply, at least in approximation. The holographic principle may point the way toward a deeper theory, one where geometry, gravity, and connectivity are all consequences of quantum information. And if that's true, then wormholes may be telling us something fundamental. Not about space as we see it, but about space as it emerges. To explore this further, we return once more to black holes, nature's deepest laboratories of gravity and quantum mechanics. These objects warp space and time so strongly that nothing, not even light, can escape once it falls inside. But the behavior of black holes raises difficult questions. What happens to the information that falls in? Does it vanish, violating quantum mechanics? Or is it somehow preserved, encoded on the surface, or released later through subtle radiation? These questions lie at the heart of the black hole information paradox, and the search for answers has led to some startling conclusions. In some scenarios, the interior of a black hole is connected to another region of space-time, a kind of mirror image, or even another universe entirely. These models often involve wormhole-like geometries, where the singularity at the center is replaced or avoided through exotic topology. One idea is that the 2 ends of a wormhole correspond to entangled black holes, their interiors joined by a bridge that cannot be crossed, but which still plays a role in preserving quantum information. Another suggests that even evaporating black holes might maintain hidden structure inside, a leftover imprint of all the particles and fields that fell in. In either case, the topology of space-time, its global structure, its hidden folds and connections, becomes central. Not just for understanding gravity, but for understanding how reality stores and processes information. Wormholes, in this context, are not just tunnels through space. They are architectures of information flow. They may represent ways the universe keeps track of itself, even when its parts seem cut off or lost. We can't see these topologies directly, but through black hole thermodynamics, holographic dualities, and mathematical models, we begin to glimpse their outlines. And in those outlines, wormholes continue to reappear, quiet, persistent, and deeply strange. All of this, from equals EPA, to Luke quantum gravity, to wormhole stabilizing energy, rests on a delicate balance between theoretical possibility and observable reality. Physics has always lived at this edge. Equations may be beautiful, internally consistent, and even predictive, but until nature says yes, they remain conjecture. A theory is not a truth. It is a question phrased in the language of mathematics. With wormholes, this tension is especially sharp. The math allows them. The frameworks suggest them. Quantum theory and gravity keep pointing toward hidden connections. But no telescope has seen one. No detector has confirmed their influence. No spacecraft has stumbled into a tunnel through space. This doesn't make them false, but it means we must proceed with care. The danger is not dreaming too big, but mistaking dream for discovery. Physicists keep working on both sides of this divide. Some push the math further, exploring what wormholes might look like in universes with different constants or under different boundary conditions. Others search the sky, refine models, develop new instruments, and look for signals that match no known source. Both approaches matter. Together, they help us feel out the edge, where possibility meets nature, and where today's speculation might become tomorrow's data. And even if wormholes are never found, the path toward them teaches us something valuable. It reminds us that not all mysteries are meant to be solved quickly. Some exist to widen our thinking, to stretch the boundaries of what we believe space and time can do. They invite us to imagine more than we've seen, but with rigor, with patience, and with humility. Wormholes may or may not exist in the way we picture them. They may never be traversable. They may remain forever hidden in quantum geometry, too small or too fast to detect. Or one day they may surprise us, in data, in gravity, or in the elegant curve of a distant light. But even if they remain hypothetical, they serve a deeper role. They keep the door open to new physics, open to unseen structure, open to the idea that the universe is more than points and distances, that it has depth, that it has memory, that it has relationships beneath the surface. Some questions stay open not because they lack answers, but because they lead us somewhere important. Not just to facts, but to a wider view of what reality might be. Wormholes belong to that class of questions. They are not just about shortcuts. They are about connection itself. And in a universe where so much is still unknown, the quiet possibility of hidden connections might be exactly what we need, not just to explore space, but to understand it. And now, the equations can rest. The diagrams fade, the light bends softly away. We've followed gravity down its quiet curves. We've stepped gently across the edge of what we know, into the hidden folds of space itself, the possible, the speculative, the quietly waiting. No need for answers now. No need to solve what remains open. There's something beautiful in that openness. A question that hasn't closed. A shape in the dark that might be real, or just the shadow of a deeper pattern still unfolding. You don't need to hold on to it. Let the geometry unwind. Let the thoughts slow. Wormholes, real or imagined, are just one way to ask something larger. How is the universe stitched together? What lies between the stars? What might connect things, even when they seem infinitely far apart? Maybe we'll find them someday. Maybe we won't. But the wonder doesn't depend on the answer. The wonder lives in the asking, in the listening, in the long, quiet gaze into the sky, open, unhurried, filled with the patient hum of space itself. So now, let yourself rest. Let time go quiet. Let distances dissolve. Let space itself soften around you, like a blanket woven from stars and silence. You've traveled far tonight, not across the galaxy, but into the deeper fabric beneath it. And wherever that fabric may lead, it holds its own calm, its own stillness, its own light. You can drift there now without needing to understand every curve, without having to see what lies on the other side. There's peace in that. Peace in knowing that the cosmos is still thinking, still turning, still quietly dreaming in its own way. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.